Hello everyone, welcome back to this course on reinforced concrete design. Let us continue our discussion. We are in week 2 and this is our 4th lecture, right? So what we have done till date is the limit state design of singly reinforced beam. Now you have seen that the moment of resistance of the section actually meets the demand, right? And that's how the design is done. Now in some cases, what happens, demand is really very high. In that case, either we can go for a bigger section. That is obviously one option, but not very scientific and of course economical. So in that case, what we do, we go for a modified version, what we call doubly reinforced beam. So as you can see on your screen, here we have schematic diagram of the beam where we have reinforcements at the tension zone. As you can see here, this is the one. In addition to that, we also have some amount of steel in the compression zone. So if we call it say AST, then we call it ASC. Obviously, due to the presence of this additional steel rebars in the compression zone, the compressive force taken by the upper part of the neutral axis is definitely more. And if that is the case, then what we have to do? We have to also provide some additional steel to counterbalance that effect in the tension zone. So that is the main purpose, and the section that we get is what we call doubly reinforced beam. In nutshell, reinforcements are provided in tension zone as well as compression zone, right? Now, for this beam, again, we are familiar with the width and effective depth, right? That definition remains same. And obviously, for equivalent, or if I remove this, say, this two reinforcement rebars, then what we get? A singly reinforced beam. And for that, we can find out mu limit, that is the limiting value. Then if by chance my applied bending moment is more than that, as I said, we can go for a section having more effective depth and width. But a better solution is to provide these additional reinforcements. Now for that, again, we have the stress strain diagram, as you can see here, to find out the neutral axis, right? Now, in addition to this D, we also define this D prime, that is the location of the compression steel. Now from the strain diagram, at the extreme fiber we have 0.0035 in the compression zone, and we are familiar with the strain in steel, okay, that we have already used in our singly reinforced beam design. So the minimum value is when we have this is equal to, it can be more as per the requirement. So we have the strain diagram here. In addition to that, we are worried of this value of strain which is acting at the level of compression steel. Otherwise, the stress profile is again what we earlier did. So we have a parabolic profile for the compression zone, and this point which is corresponding to 0.002. Beyond that, there is a straight line, and then finally this value of design stress also we are familiar with. So with these modifications, let us see how we can find out relevant sectional capacities. For that, our task is to first find out the position of the neutral axis. So what we do, we equate compression and tension, but in the case of compression, now we have two components. One is coming from concrete, another is coming from steel. How to evaluate that? It's very simple. So for concrete, this part we are familiar with. We did it for the singly reinforced beam. Now, when you talk about this part, it actually considers the section, say we have neutral axis here. Then above the neutral axis, the complete section under compression, and that concrete we consider to evaluate this force. Obviously, we have considered one area of ASC and that we subtract. Then what we do? We add the compressive force on this compression steel, and that is FSC, that is the stress on this reverse, which we will see how to find it out, times ASC, that is the area of the compression steel. Now this is equal to 0.87 Fy times AST, that is the amount of tension in the tensile steel at the bottom. Now if we simplify this expression, then what we have here is this expression. Now from this expression, what we can see, we have XU here, then we have FSC here, and these are the two quantities that we have to fix. We are mainly looking for this XU, that is the first objective, but for that we first need to quantify this FSC, that is the stress in the compression steel, which is here. How to do that? Let us refer the strain diagram first, because that is the linear diagram we have to deal with. So epsilon SC, that is the strain here on the compression steel, divided by XU minus D prime, that is the distance from the neutral axis, is equal to the strain in the extreme compression fiber divided by XU. And from that what we get, epsilon SC is equal to XU minus D prime by XU times 0.0035. So what you can see, we can find out this epsilon SC, and the moment we find out epsilon SC, from that we can also quantify the respective stress in the steel. That we'll do in a minute, but for the time being, we as of now don't know this XU. Again, epsilon SC depends on XU. From epsilon SC we find out this stress along the compression steel, and then this is a cyclic process. So we solve this using trial and error. That is the main trick we adopt here. We'll see how we implement that in a minute, but the problem is pretty simple. The same way we balance compression with tension, but because we have a steel in the compression zone, we have additional components in the compression side, right? Now, what you can recall from our previous discussion, for a balanced section, if we have an under-reinforced section, we have evaluated XU limit. And that depends on the grade of steel, and for different grades we have evaluated this, which was for 250 grade steel it is 0.53D, and then for 500 it is 0.460. So what we do, we start with this step 1. We first calculate XU limit and assume that this is the location of the neutral axis. Then once we assume that, we can find out epsilon SC. And we already know the stress strain behavior of different steel. These are known to us. So for different stress level, we can find out a respective strain. So what we do, we use this chart. Then from this chart, we find out FSC using interpolation, right? In this chart, this FYD is nothing but the design yield stress, which is 0.87 Fy, right? Okay. Now, the question is, if the epsilon SC, that is the strain in the compression steel, lies between the values given in this table, then what we do, we go for linear interpolation, right? As usual. Now, if epsilon SC is less than these limiting values, which are here, then what we do? Then we use this direct expression between stress and strain, and we find out what is the level of stress in the compression steel. And then once we do that, we come back to this expression again, because now we know FSC, and then we can revisit the expression to find out what is the value of XU. So in the next step, if XU in this step 4 is not equal to XU1, obviously then we have to reassume that this new X2 is actually basically the level of neutral axis. And then we have to again repeat the procedure from step 2 to step 4. And that's how we carry out this iterative procedure in trial and error, and then finally we converge to the level of neutral axis. So for that, let us take an example. So what we do, we determine the position of neutral axis for this given section. So what is given here? The width of the beam is 360 millimeter. Total depth is 700 millimeter. Then D prime is 60 millimeter. The grade of concrete is M30 and steel is Fe415. The effective cover is also 60 millimeter. We have 4 16-5 steel in the compression zone and then 5 25 steel in the tension zone. So let us start the iterative procedure. In the step 1, what we do, we find out XU limit that we can directly find out for this given information. So in our case, what we have, XU limit, which is our first assumption, that is XU1, is 0.48D. That means we have 0.48 times this D. Actually, this will be, there is an error. So total D, capital D, that is the total depth of the section minus this effective cover. So that is the effective depth. And from there, we find out that XU1 is 307.2 millimeter. So that is the first estimation. So what we'll do, we'll verify whether it is correct or not. If not, definitely we'll iterate the procedure. So in the step 2, what we do, with this information, with this value of XU, we solve the strain in the compression steel, and that is 0.00281. Because we know already D prime, which is 60 millimeter, and the extreme fiber in compression having a strain of 0.0035. Then once we have this information, that is the strain in the compression steel, we can refer to the stress strain table, and from there we can find out the stress value corresponding to this level of strain. And for that, we have done an interpolation between the two values here, as you can see. And then ultimately what we get is the stress in the compression steel, and which is 352.23 Newton per millimeter square. Now, once we find out this stress, we can revisit the equation for XU by equating C and T again, and then find out the value of XU. That we'll do in a minute, but the procedure is very simple. So ultimately what we get is the XU, which is 157.85. Obviously, this is not the first estimate of 307.2. So then what we do, we go for the second trial, and we assume that this new value of XU is the XU2, and then repeat the same procedure. So we find out the strain in the compression steel, which is in this case 0.00217. Then again we go for an interpolation, find out the stress in the compression steel, which is 333.97 Newton per millimeter square. Then again recheck whether this assumption of this XU is correct or not. And for that, again with this new value of stress along the compression steel, we revisit to calculate XU. Now what you see here is the new value of XU is 161.67 Newton per millimeter square. Obviously it is not same, but what you can notice is very close. As opposed to earlier, we started with 307.2 and we ended up at the end of first iteration is with the value of 157.85. So what we can do here, we can go for the third iteration, and then after 1 or 2 iterations, it will converge and you will see the exact value of XU. Now, obviously, it will be less than this value, so we can have an assumption that XU is equal to 160 millimeter. Right. So this is the procedure that we adopt to find out XU if we have a doubly reinforced section. Now, let us move further. So for this section, our next task is to find out the moment of resistance, because this value of moment of resistance represents the capacity of the section, and with the help of that capacity, you have to balance the demand that is coming from the structural analysis that you already know. Now for the moment of resistance, again, we can start with this doubly reinforced section and split it into two halves. The first one is obviously singly reinforced section, as you can see here, where we have AST1 as the steel in the tension zone, and then we add with this another section which is having the additional steel ASC provided in the compression zone and AST2 provided in the tension zone. And for that, we can draw the stress block. As you can see here, the first stress block corresponds to the singly reinforced section we are familiar with. We can find out this C1, we know T1, and the distance between these two is the lever arm 1, right? Then for the second case, we can find out the C2, that is the compressive stress along the steel reverse in the compression zone, and then we can also calculate T2 and the lever arm LA2. We'll do that in a minute, but the idea is pretty simple. We start with this doubly reinforced section. We split it into two different sections. For individual section, we find out the moment of resistance. So for the first section, we have MR1. For the second section, we have MR2. So you simply add them up to get the total moment of resistance of the section. So that is the combined moment of resistance for the complete section. For that, again, what we do, C1 times LA1, that is for the first section, which is marked here as 1, as you can see here. And then we have the second section, and for that, we have C2 times LA2 for this second section. So in the first approach, what we do, we start with the compression side and we find out the moment of resistance. Now, this estimation is pretty simple. The first part, 0.36 FCK times XU limit times B, is known to us. We have already done this for the balanced singly reinforced section, times D minus 0.42 XU limit is the lever arm. So this is the first part of the moment of resistance. For the second part, what we do, we find out the stress along the compression fiber, and this is FSC minus 0.45 FCK. That multiplied by the area of steel in the compression zone. So that is the force times lever arm is D minus D prime. D prime is basically here, and D minus D prime is the second lever arm for the two forces in tension and compression in the second section. So if we add them up, we get the total moment of resistance. That is pretty straightforward, and we will find out, we'll see how to evaluate this for a given section when we'll take some example. Now, we can also find out this moment of resistance from the tension side. For that, what we have to do, we have to first find out the net compressive force acting, and we take the average of this. We have two components of the compressive force, C1 and C2. They are acting at a distance Y1 and Y2. As you can see, it is marked here. So what we do, we take the average of these two, and then we find out this Y bar. Now Y1 is known to us, that is 0.42 times XU, which comes from the singly reinforced section, and then Y2 is the D prime, right? Now, once we get this, what we have to do is the tensile force times the lever arm now, and the new lever arm is nothing but D minus Y prime. Y prime we have already figured out from this expression. Now, for the tensile force, we again can easily calculate that it is 0.87 Fy times AST times the lever arm gives us the value of moment of resistance. Now, we can calculate this moment of resistance based on compression or tension, but obviously we prefer to go the first way, where we use the compressive force in concrete as well as steel to find out the moment of resistance. Okay, so let us take an example. Our task in this example is to calculate the moment of resistance. So now B is equal to 360, capital D is equal to 700, then effective cover at the top and bottom are both same 60 millimeter. And we have 416.5 in the compression zone and 525 in the tension zone. The concrete used is M30 and the steel is Fe450. Now, for this combination, what we had in the previous example, we used the XU that we have already solved, and the approximate location of the neutral axis is 160 millimeter from the top. We can actually continue the iterative procedure that we discussed earlier to get an exact value, but let us carry on with this value and let us see how we can calculate the moment of resistance of the section. So from this XU, the first thing we do is the strain in the compression steel, that we use again the same formula and find out the strain, which is 0.00218. Once we find out strain in the compression steel, our next task is to find out the stress in the compression steel, and that we can easily find out using interpolation that I have already explained. So ultimately what we get, FSC is equal to 334.62 Newton per millimeter square. Now once we get that, we can easily find out the moment of resistance, which has two parts, C1 times LA1 and C2 times LA2, that I have already explained. So using the expression here, we can find out the moment of resistance. Just we need to put these values which we have already evaluated, and then ultimately the moment of resistance we get in this case is 506.1 kilonewton meter. So that's the net moment of resistance due to additional steel in the compression zone, and that's the only additional thing we have compared to singly reinforced sections. Okay, so if we summarize the total steps in this design of doubly reinforced section, here you go, here are the different steps. So we start with the design of this doubly reinforced section. Of course, we go for this doubly reinforced section if the section size is restricted and when we cannot meet the external demand with the value of B and D that we select for this singly reinforced design. So what we have is normally section side is already known. Our task is to calculate AST, that is the amount of steel we provide. So the steps are as follows. Again, the first step is we have to calculate the external demand. For that, we first identify different loads, dead load, live loads, and their effects. For example, if you have a simply supported beam which has its own weight, and then it may have some live load which is acting as a uniform load. So this is the live load, plus the beam may have this dead load, and then under these loads at the middle we'll have maximum bending moment. So we need to find out those bending moments with appropriate factors. Now once we do that, in the next step what we need to do, we need to calculate mu limit, that is the limiting value of the sectional capacity for a singly reinforced beam. And mu limit, as you recall, it is QBD square. So Q depends on different grades of steel, and we have already discussed this earlier, the values of Q for different grades of steel, and of course we need FCK value also. So in the step 3, if we have BMU is less than mu limit, then obviously we don't need to go for a doubly reinforced beam. We can easily go for a singly reinforced beam which is also under reinforced as far the neutral axis location is concerned, because we have the external demand is less than the critical capacity. Then what we do, we can find out AST easily from this expression. We have done it earlier also in different examples. But because we are going for doubly reinforced section, obviously we will have the external demand is more than the limiting value, and that's the reason we have to provide additional steel in the compression zone. and hence we get this doubly reinforced section. Okay. Now, for that what we have to do, first we calculate AST1, and AST1 how do we calculate? Of course, the first section we consider, first part is the limiting case. So AST1 is nothing but AST limit, and for that again this formula we have already derived this expression earlier. Now, once we find out AST1, that is the amount of steel required in the tension zone for this first section, recall we split this doubly reinforced section into two halves, the first section and then the second section where we have this additional steel in the compression zone. So for the first part, we have figured out what is the AST1. Then we can also find out the amount of additional external demand we have to meet with the steel in the compression zone. And for that, how do we do? We have already evaluated external demand. We know MR1, which is MU limit. And from these two, we can figure out the additional demand that we have to meet with the additional sectional capacity arising out of this ASC. And to balance ASC, we have to provide this additional steel in the tension zone, AST2. So first we calculate AST2 because we already know this additional moment requirement. So this additional sectional capacity will be T2 times LA2. So this T2 is nothing but 0.87 Fy times AST2, and the lever arm is D minus D prime, which is here. From this equation, you see we can calculate AST2 because that is the only unknown we have. So we can calculate AST1 and AST2, that is the total amount of steel. So in the tension zone, the total amount of steel we have figured out. So AST1 plus AST2. Now what we have to do, we have to find out additional steel ASC from where, because we know AST2, from this information we have to find out ASC. That we'll do in a minute. Let us see how we can do that. It is here. So in the seventh step, what we do, we again balance C2, that is the compressive force in the steel provided in the compression zone, which is equal to the T2 coming from AST2. And from this equation, we know what is C2. C2 is given here. The stress, which is FSC minus 0.45 FCK, times ASC is the amount of compressive force generated over this steel in the compression zone, and that is equated by 0.87 Fy times AST2. We have already figured out what is AST2. So from this expression, we can find out ASC. And our problem is completely now solved because now we know ASC, AST1, AST2. So we can provide the steel, suitable diameter steel in the compression as well as tension zone. Now again, you have to recall that once we find out the amount of steel, we have to check the minimum requirement or the permissible limits as per IS 456. So this is the AST minimum we have to find out, and the maximum value of AST is 4%. So this is the AST maximum. We have to ensure that the amount of steel we provide that satisfies this criteria, and then the design is done. So these are the 8 different steps we have to follow one by one to design doubly reinforced section. Now let us take an example. So design a section for factored bending moment of 110 kilonewton meter if size is restricted to 250 by 380 millimeter and the effective cover is 50 millimeter. Concrete is M20 and the steel used is Fe 450. So let us follow the steps that we have already described. So the first step, factored bending moment, which is given here. Sometimes it is not given. If not given, then we have to first figure out what is the factored bending moment. In this case, we have the factored bending moment as 110 kilonewton meter. Then what we do, we go to the next step. We find out MU limit, which is 0.18 FCK BD square for the given materials we use. So we find out mu limit, and which is 75.14 kilonewton meter. Obviously, the applied bending moment is more than this limiting value, and therefore our our balance section, singly reinforced balance section, is not sufficient enough to cater this demand here. We have to go for doubly reinforced section because we cannot increase the depth of the beam. There is a restriction, and due to that reason we have to provide additional steel in the compression zone, and that will be balanced by some additional steel in the tension zone, and hence we will get this doubly reinforced section, right? So what we do, we calculate the AST1 in step 3, that is for the balance section. So it is AST lim, and that we can easily calculate. It is 0.414 FCK by Fy times XU limit times B. And from this expression, we find out that the AST1 is 790.1 millimeter square. So now we know the first component of the tension steel. Next is we have to find out AST2. For that, we go to step 4. Here first we find out the additional capacity requirement arising from the extra bending moment that is coming from the external sources, which could not be addressed by mu limit. Okay. So MR2 is nothing but the difference between these two. So external demand is here, that is 110, and the singly reinforced balance section is offering 75.14. So the difference between these two will be taken care by AST2. Now we have MR2. So in the step 5, we can calculate AST2 just by equating this force with the moment caused by this T2. So MR2, which is 34.86 kilonewton meter, that will be balanced by this quantity 0.87 Fy AST2 times D minus T prime. So if we put all the values, the only unknown here is AST2, and we can figure out the requirement here is 344.8 millimeter square. So effectively, we have to provide 790 millimeter square and 345 millimeter square. These are the two different steels that we have to provide, and if we combine, then we get basically AST, that is the steel in the tension zone. Then what we have to figure out is the amount of steel in the compression zone, and for that what we do first, we find out XU limit. That is the first task. So in our case, XU limit is 158.4 millimeter. Then we find out respective strain in the compression zone. So epsilon SC, that is the steel in the compression zone, and epsilon is the strain. Here we know XU, we know D prime, so we can calculate epsilon, and which is 0.00239. Then what we have to do, we have to find out FSC, and that we do using an interpolation formula, which is here. So epsilon SC is 342.06 Newton per millimeter square. Now what we do, we equate C2 with T2 to find out ASC, because that is the only unknown we have in this equation. We already know AST2, so from that information we can find out ASC. And the ASC is 373.77 millimeter square. Once we find out steels in the compression and tension zone, then first we need to check the minimum and maximum requirements. So we first find out AST, then we find out AST minimum using this expression, and in our case it is satisfied. Then we also find out the maximum allowable limit of 4%. That limit is also satisfied by the amount of steel that we have evaluated from the demand, right? Then we have to provide the amount of steel, because you cannot leave this at this stage. This is the amount of steel, you cannot leave it there. You have to identify the diameter of the bars and how many bars you have to provide. And we have already explained that you have to maintain sufficient distance between two bars, and this distance preferably 60 to 70 millimeter, and accordingly you have to provide the number of bars. So what we provide here is 225 diameter bar in the compression zone, and then we have a combination of 225 diameter bar in the tension zone plus 116 diameter bar at the middle. So that's how we design the complete section to meet the requirement of 110 kilonewton meter of moment. So this example completely shows you how to solve the doubly reinforced section, how to evaluate their location of the neutral axis, and then systematically find out the moment of resistance. We prefer to evaluate moment of resistance from the compression, and then we have to find out the steels in the tension zone. We have to find out AST1, AST2. There is a small error here, it should be 2. So then we have to find out ASC from AST2, and then finally we have to design the steel. That completes the design. So what I suggest, you go through these notes, and if you have any doubt, do let us know. Otherwise, you can also practice a few problems following the steps that I have already discussed here in this class. Thank you very much.